see, I mean, is the font good? No? All right, we're going to have some code here in a little bit, so I might change it. But we're going to change gears a little bit. So instead of talking about how to do a specific analytic, I'm going to talk to you about Spark, like another framework. And particularly, I'm going to focus, this is a Hadoop user group, I'm going to focus on Spark on Hadoop. So everything that I put together, sort of, we're going to look at the Enron email data set and sort of put that into Avro format and then analyze it in Spark. All the code and everything for it is on GitHub. The presentation is on GitHub. So you can do the Spark mail, just the code there. If you're interested in actually running Spark, just to try it out, kick the tires. I put together a little Docker image that has, I built on somebody else's Docker image that has a Hadoop 2.6 on it, and just put Spark on top of it, and like a subset of the Enron email data set, so you can actually just play around with that, try it out, see how you like it. So talk overview, compare Hadoop, Spark, and then talk about the central Spark abstraction, which is this resilient distributed data set. Talk about Enron email, how we put it into Avro, talk a little bit about Avro, and then do an actual analytic, and do it in Hadoop, with MapReduce, and do it in Spark. And just sort of core Spark, none of the add-on packages, and sort of give you a feel for what that looks like. As we're going through the actual analytic, I'll show you how to install Spark, how you can run it on top of Yarn, and then sort of the interactive analytics through the Spark shell. I'll show you Spark Web UI, and then sort of the central abstraction, RDB, error RDB functions, and double RDB functions, which sort of make your programmer life nice. I mean, they're nice high-level APIs to do things, and then some resources. We'll wrap it up with that. If you have any questions, please, it doesn't have to be all one way. At any point, just raise your hand, ask away, and we'll try to make it more clear. So I'm Marcus Dale. I'm currently working at DoD. Before that, I was at the Johns Hopkins Applied Physics Lab at Raytheon. I was a naval cryptology officer once upon a time. And I also sort of been teaching quite a bit. So while I was in the Navy, I used to teach Java and Solaris System Administration. Then I taught the distributed development in the World Wide Web for the Johns Hopkins program. Then thought I wanted to get my PhD, but I'm like Don, I never quite finished. But that's where we sort of all met up. I took all the coursework and started some research, and I was like, wow, that research stuff was really time intensive. So we'll do something else. Play around with something. So Hadoop ecosystem. So by now, 2015, the Hadoop idea has actually been around a long time. So it all started, of course, from Google with the Google file system in 2003, and the MapReduce paper in 2004. Google just gave us the papers. But Doug Cutting at the time was working on a search engine called Notch, sort of distributed crawler for the World Wide Web. And he's like, wow, those are some pretty good ideas. Let me scrap what I had in terms of trying to distribute my computation and try to implement some of these algorithms, this GFS. And MapReduce, we called it Hadoop. Yahoo saw it, and they're like, oh, this is good stuff, come work for us, and we'll still make it open source. So Hadoop, and actually before I speak any further, who's doing Hadoop right now? I sort of assume everybody is, since it's a Hadoop user group. Is that good? Who's doing Spark? Who's played around with Spark? Anybody? Yeah, a couple people. Anybody ever played with Scala? Okay, a couple people. All right, so do it nice and slow, so step by step. All right, back to the Hadoop ecosystem. So you have HDFS, scalable storage, right? I can take my whole cluster and make it look like one big drive. And I use replication, typically like a factor of 3. I store each file block 3 times, just so I get my redundancy. Then on top of that is, so I can not just only store things, but also have a MapReduce batch processing algorithm Whereas if you can sort of implement your computation in terms of a mapper and a reducer, then the framework will take care of scaling this out for you. And up to Hadoop 1, that's all you had, map reduce. That was your parallel processing of choice. But with Hadoop 2, they introduced this thing called Yarn, yet another resource negotiator. And basically, it's a resource manager, and they took MapReduce and made it a MapReduce application master. So that thing knows how to do MapReduce, but it's just something that Yarn schedules. So Yarn can now schedule other frameworks. It's a general scheduler, resource allocation. And one of those things you can run on top of it is Spark, and we'll see how that works. Now, MapReduce being written, it's a Java API. That's pretty low level for a lot of people. I mean, Kristen, you were saying you were using Hive, so if you want to do SQL, that's your flavor of choice. You have Pig, another DSL, and then like cascading, scalding, crunch, and there's lots of others. But basically what you have is so these high-level languages that get translated into MapReduce, but you can write at the higher level and therefore be more productive. If you want to do graph processing, you can do it as MapReduce, but typically that's very inefficient. So you have like things like Giraffe. If you want to do real-time streaming, you add something like Storm to your cluster. If you want to do machine learning, you have Apache and Hadop and some libraries. So there's a rich ecosystem, which is fantastic. It's very well established. The downside, though, is you got to install all that stuff, and then you got to maintain it. And you got to learn about it, right? There's the cognitive complexity of like, well, how does this framework work? And how is this framework? What are the assumptions? What are the basics? And it's all very heterogeneous. So it takes a lot of time to do that. MapReduce is batch only. So you submit a job, and then it runs in the cluster. Depending on how crowded your cluster is, you might get different response times. And there's definitely no interactive shell. So one of the things, if you've ever done Python programming or Scala programming, you have this shell thing, and you can write a little code and it executes. Definitely nothing like that. The other problem, of course, is if you do just one MapReduce job, perfect. But what about if you have a job that needs to iterate? You have like a machine learning algorithm, and you have some sort of ending condition, some delta you're trying to get to. You might have to run very many iterations. Between each MapReduce, you write back out to HDFS just for your next iteration to read that back in, the thing that you just wrote out, and do it all again. So that's not as efficient as it could be, although like frameworks like Apache Tez is trying to find a solution for that. And then overall, it's very low level. I mean, you have a map and reduce, and you've got to translate your problem into that framework in order for it to scale up. So those are some of the challenges you have. So why Apache Spark? So Apache Spark, much newer. So it started in 2008, 2009 at Berkeley. They were sort of they had this distributed scheduling system, Mesos, and they wanted to have an application to run on top of it, and they sort of cranked out Spark, and had some different trade-offs. So in Hadoop, the redundancy was, well, I write the blocks out to disk, and I replicate the blocks. If one of the disks goes down, I can read that from somewhere else. Well, Spark was saying, hey, we got much faster processors. We have a lot more memory now. So my redundancy, instead of going back to the file system, is I'm going to remember, like for each cluster, each machine in my cluster has a little partition of data. I'm going to remember how that partition was generated. i.e. it was read somewhere from disk, and then I apply all these transformations to it, and that's how I got to that partition. If that particular partition goes down, I'm just going to recompute it from scratch. Either all the way from where it was stored, or it has many different input sources. But that's my redundancy there, and we'll see that a little bit with the resilient distributed data set.
Hey, Mark.
Yeah.
I have a question.
Yep.
What are some concerns when you have like something that's derived off like an aggregate, where it's basically, in order to rederive that piece, it's like the entire data set? Does it just like go and rerun the entire pipeline, I guess, at that point?
Yeah, it would have to be run. Okay. Yeah, so I mean, sometimes the penalty can be pretty draconian.
Okay.
You know, and they talk about narrow dependencies versus wide dependencies, like if you have a bunch of shuffled aggregates.
Yeah.
Yeah, sometimes you have to go all the way back.
Okay.
Now, one of the things you can do is checkpoint things. So you write things out to disk. Like you know, you're like, oh, I did a lot of work right now. Let me checkpoint right here. And so then you only have to work from that checkpoint.
That's fine. Something else. Thanks.
So the big thing is program productivity. We give you a higher level API and still make it scalable. And it's a little bit better suited for iterative algorithms because instead of writing things out to disk, I can keep them in memory, I can cache them. And so I can, you know, data science being a very explorative science. You want to run a lot of experiments. A lot of times you don't know exactly what you have and you want to try different things out. Well, you can just load the data set into memory once and then try out, you know, different algorithms, different approaches, and until you have what you really want, and then put that into production. And that's where the Spark shell, this interactive data exploration, is really nice. And of course, you know, all your Hadoop investment is still there because you need the scalable storage. So Spark doesn't deal with storage per se, but it will happily read from HDFS. And it will happily use Yarn as its resource manager and run as an application on top of Yarn. So you can still use your cluster. You will have some Hadoop jobs. You might have some Spark jobs. They'll happily coexist and basically use the same resources. And, you know, like I said, it can read and write HDFS natively and like a lot of other data sources, more every day. And then, of course, you have the buzz. So this is what got me last year. You know, I'm like, Spark, what is this Spark? I see it everywhere. And so I bought the Apache. O'Reilly put out a book, Learning Spark. It was in early alpha, like last September or something. So I started reading about it and said, oh, that's pretty neat. And then I was scheduled to go to the Strata Hadoop conference. And they have a Spark tutorial. Oh, great. All right, I'm signing up for that. And, you know, I signed up pretty early, got in, and then heard there was like this long waiting list. Like they took like 500 people in, and it was this huge room, and they sort of did an all-day tutorial. That was pretty good, and that was a nice API. And so when you look at Google Trends, you know, like these search terms, I mean, there's a lot of people out there on Spark. I'm subscribed to the Spark user group, you know, all the mailing lists. They have like over 10,000 emails since I subscribed like November timeframe or something. I can't keep up with it, but you know, it's like there's a lot of stuff going on. So what is Spark? You know, so Spark is combining a lot of pieces, and this is from Databricks, which is sort of the commercial company that was founded by the people who did their dissertations on Spark at Berkeley. So you have the Spark core engine, which is sort of the substrate that pulls it all together. And that's where the RDB lives and all the core API. And then on top of it, you have these other APIs and libraries that sort of feel very homogeneous. You know, it's the same type of abstraction. You have Spark SQL, which allows you to do like a Hive, you know, like a SQL type thing, but it's also high-level domain-specific language. So if you have structured data, like records with fields, you save them in Parquet files, it really boosts your productivity. It has like a nice DSL that allows you to read these things. If you want to do more real-time processing, a non-batch, you want to do, you know, like as data comes in, you can do Spark streaming. And you know, under the hood, it still has that RDB abstraction that everything has. And if you want to do like seconds worth of latency, Spark streaming is good, but it still does like micro batch processing. It batches up a bunch of events into windows and then allows you to process them from there. If you want to do machine learning at scale, it has its own machine learning library, MLlib. If you want to do graph computations like PageRank or something like that, it's GraphX. And apparently the latest thing, I hadn't actually seen that until I went to their website, Spark R. So they're going to have R running on top of Spark, which is still in the alpha stage. So I have not played around with that. So the central abstraction in Spark is that resilient distributed data set. And basically it's distributed across your whole cluster. It's immutable. Once you create an RDD, you can't change anything from it. You can create a new RDD that's based on the old RDD. But like the old RDD is still, conceptually still there. It's immutable. Resilient is like each partition remembers how it was computed. And so it has this lineage information. And if that partition goes down, the driver will notice, and you can recompute that particular partition. RDD operations overall are divided into two major groups. You have transformations on RDDs. So you have your original RDD you read from like a file system. Then you do a transformation on it. You pull out certain data, or you're changing certain data. But remember, it's immutable. So when you're doing that change, you're actually creating a new RDD. But under the hood, since everything is immutable, they can apply all these optimizations and everything. And actually, when you're doing transformations, nothing actually gets computed. So it's lazy. It just remembers, oh, you can do that. Oh, you want to do that. Yep. Oh, you have like 10 transformations. When you do an action, at that point, it looks at all those transformations you were trying to do and sort of optimizes how those transformations are done. So instead of doing one thing and then the next thing, if your action is take first, then it knows it only needs to get one element, so it can really optimize what it's trying to do. So you have these, and these optimizations keep getting better. So then the actions cause the transformations to be executed, and the API, you have a Scala API, so Spark natively is written in Scala, but you also have a Java API, a Python API, and I guess R is coming. So there's some pretty rich functions.
Curious, how is the lineage actually persisted? Is it everything decomposes to Scala and just like the actual statements are just reinterpreted on the fly? Do you know how that actually works?
I do not. I mean, basically, at the very end, there's like a 2 debug string on RDD. So it's sort of like it has different RDDs. So I assume internally they know about the previous RDD and how it was computed, because there's different types of RDDs that we'll see later on. But I haven't actually looked at like the bowels of how they're actually implementing that. But it's all Scala and Akka and some Netty, and they keep trying to optimize it, make it faster. So, all right. So what I want to do tonight is basically look at the Enron email data set and run an analytic over that. So Enron, if you remember that Enron scandal, at that point, like the FCC compelled them to publish, I think it was for like 150 people, all their emails. And so it's this huge email data set that's out there in the wild. There was sort of a version that I got from Carnegie Mellon that sort of cleaned up some stuff, took out PII and embarrassing things that didn't really need to be there. Some of them are still there. But essentially, they give you a big tar.gz file, and it's these directory. It's a big directory. And under the directory, you have the user folder, and then under the user folder, like whatever email folders that user was using, they're underneath. And then at the very bottom, you have text files that essentially have these headers, to, from, subject, and some other mail headers, and a line break, and then the actual body. No attachments from this data set, although there's other Enron versions that have the attachments. There's about 500,000 files. Most of them are really, really tiny. And Hadoop doesn't like tiny, tiny files. So, if you just were to sort of do the file input format pointed at it, you have like 500,000 splits. It would take you longer to schedule those things than the actual processing for each tiny email. And, we don't really want our analytic code to worry about parsing each email, because there's, the idiosyncrasies there. So I decided to put this into Avro format and store them together in this big container file and have these mail record objects. So what's Avro? So, and why? One of the most common data formats, I think, right now is sort of just straight out of JSON. And that's a fine format, except, if you want to store binary data, you need to do something to encode that. Of course, if you're doing Hadoop, Hadoop writables are great, right? That's what they were invented for in sequence files, but they're very, very Java-centric. So Doug Cutting, the guy who came up with Hadoop, and Lucene, decided, hey, let's have this binary serialization, deserialization format, Avro, and I'm going to make all these different language bindings, so you don't have to use Java to process your data. And I'm also going to put the schema at the top of each file, so you know, and then all the records in that file are of that schema. So if you give me a file, I can figure out sort of what's inside it. And with that schema, you can do generic processing, or you can generate a Java class from that schema that has all the fields that your schema says it needs, and that's what I did. So I have a big Avro container file that has all the Avro records from all those 500,000 emails, and I let Hadoop worry about splitting those up into blocks, and I'll be able to read it in. There's also compression, and then of course you have splits, where Hadoop breaks this up into all the different blocks. So here's the schema that I chose for this mail record. So I have a UUID, just generated for each one of these mail records. Every mail has a from, but then two copy and BCC sort of optional fields. Like some are all BCC, sometimes so you never know which ones of those are there. So essentially what those fields are saying is, I have a to field, but it could be null. If it's not null, then it's an array of strings. And those strings, each string is an email address of where that thing was sent to. Has a date when it was actually sent, a subject, and then different mail messages had different fields in it. So I just have this sort of catch-all mail fields, and these header fields that have like a tag, colon, and then a value. Like if they're not one of these other ones, I just throw them in the mail fields and have the body. And for this email set, I didn't have attachments, but I was also using this exact same thing to process the Jeb Bush email data set, and it had lots of attachments. So I have that in Meetup.
What's the Jeb Bush email data set?
So when Jeb Bush decided to run, he published his emails from his time as Florida governor. Except like the first analytic I basically ran on it was I was doing a regular expression searching for social security numbers. And there were like, I just did a couple of months, around the Dimple chats time frame. And I found like 19 emails where people had sent him emails saying, they couldn't do this or couldn't do that, and here was their social security number. So, just as a note to self, like most governments have this FOIA, Freedom of Information, and they have it at the state level too. Don't send anybody at the state level your social security number, or anybody really, but, so yeah, I'm sort of looking at somebody from Georgetown to do a PII paper on, how something like that can be prevented. So we use the exact same schema. So now that I have my Enron email data set, I want to do mail folder statistics. So at CMU, they had a project that I think was like Halo. It was like personal assistants that can learn. And one of the things that was of interest is like, how do people organize their mail? How many folders do they use on average, and how do they put mail into that folder? Well, with the Enron email data set, they had, just that. So what we're going to do is we're going to find out, what's the least amount of email folders anybody has, what's the most amount of email folders, and what's sort of the average number of folders that a user has. And, with each email record, I basically have, based on the directory structure, I'm able to figure out who the username is. That's sort of the top level directory under the mail directory. So this is Kenneth Lay's email, one of the bad guys who actually went to prison for the Enron thing. And then all the folders are underneath, and they could be nested multiple times. And so, and each folder, of course, could contain multiple emails. So we can get that out of the mail fields. So if we wanted to do this in Hadoop, and I do have the full analytics analytics, so as an attachment here. But what we do in our mapper is we read each email record using the Avro key input format. And so the key value would be an Avro key that contains a mail record. And then, the value, so the mail record has all the information in it, so the value is just a null rifle. And then I go through there, I go into the mail fields, I pull out the username and folder name, and then I just emit that as a key, is the username. And then the text, the value is the folder name. So basically I have the username as a unique key, and then all the folders from all the emails. Now there's going to be a lot of duplication, right? If I have like 1,000 emails in the business folder, I do like Kenneth Lay business 1,000 times. And we'll deal with that on the reducer side. So in the reducer, I want to create a unique folder names. And so I use a set. Set only contains unique things. And so as I iterate through all my folder names, I just put them in the set. And the set eventually is going to have just the unique folder names. So the set size is really the folder count for that particular user. Then I keep adding up all the set sizes because, in this case, I'm just putting it through one reducer, so not scalable. But I can count up the total number of folders that were observed by adding up all the set sizes for all the keys that I see. And then the total users are just the one-up counter for each key, and I keep track of the minimum and max. And then in the cleanup method of the reducer, so when the reducer has seen all the processing it has done, at that point I can just write these things out, and sort of my average is just the total number of folders divided by the total users. And I just sort of write that out as a text string. Nothing fancy there. Then on the driver, I just need to set the Avro key input format, set the key schema to my mail record schema, set the number of reducers, in this case 1, which is the default, so I didn't really need to do it, and an output format to write this back out. So that's what I do in Hadoop. But, you've probably done something similar to that. Now, how would I do the whole thing in Spark? So the first thing I got to do is I got to install Spark. So let's say I already have Hadoop installed. Well, the way I can get Spark, so it's really nice, is I download it from the Apache Spark site. I got to map my Hadoop version. So if I'm running Hadoop 2.6, I want to download the version for Hadoop 2.6. Now, if you're using the special Hadoop version, the special distribution, download the source code, and then build against your particular version. You untar it on an edge node. What I mean by edge node is just a node that has access to your cluster. You don't need to install it on every node in the cluster, just on one edge node that can talk to your cluster, and the cluster has to be able to get back to that edge node. And it has to be able to talk to the resource manager. So wherever your resource manager is running, because that's where the Spark job gets submitted to. And then the resource manager starts the Spark application master, and then resources start flowing from there. You need Java, and then you can do one of two things. You set the Hadoop conf directory, and wherever you keep all your Hadoop configuration sites, like your Yarn site, all those Yarn XML, those configuration things, just set that configuration variable. Or you can go into your Spark installation. There's a file called spark environment.shell, and you set it in there. So that gets read before it starts. Or, it comes bundled with all major distributions now. So, if you don't have a Hadoop from scratch, you have one of these distributions, Spark's already there. So now, how do you run Spark on Yarn? So Spark essentially has a driver. So that's the thing that coordinates all the work that needs to be done, keeps track of all your RDPs and the partitions and everything, and then it has a bunch of executors. On Spark, you would have a Spark application master, and you can choose whether you want to run the driver with your Spark application master, or you could run the driver on your edge node. So then you can submit jobs to the Yarn resource manager by just using the Spark submit command. And you set the master either to yarn cluster, that means you're going to run the driver in the cluster, or you can set it to yarn client, and the driver will run on your edge node. Or you can run it as interactive shell, which is what we're going to do. So if you wanted to run things as the interactive shell, you call the Spark shell command. And the Spark shell command has a bunch of options. So the master here, I'm doing yarn client. So I'm actually doing the driver on the client side. I say how much memory I want for the driver. I say how much memory I want for each of my executors. I say how many cores I want to use for each of my executors, which is essentially how many threads each executor runs and how many tasks it can do in parallel. And I choose the number of executors. And I notice here I'm running on this machine on Docker, so everything's one and little. But like if you have a big cluster with 100 machines, you can choose 100 executors and things will run nicely in parallel at scale. So you can set those numbers. I'm not going to get into like serialization. Like by default it uses Java serialization, which is sort of slower, so they recommend using this thing called cryo. So there's some things you got to set up for that. And then you just give it the jar that has all your code. And that will start up a Spark shell. And now with the Spark shell, I can go to town, go program. So let me start with Spark shell. So I already started, so this thing that you're seeing here, can everybody see that okay? Is that big enough in the back? Yep. So I already started up my Docker image, and you can see I started name nodes, data nodes, secondary name node. So it has resource manager, it's all running on this one thing. And then here I just have this script that I did, start Spark, and it's essentially what I just showed you, plus all the cryos. So what I'm going to do is I'm going to start Spark. Yeah, in Docker. Yeah. All right, so it comes up. Now, normally you'd see it's view like 100,000 messages, but I set the logging to just warn, so we can get some actual work done. And so it's starting up behind the scenes, and now it tells us it's ready to go. Now, if you have a program in Scala, this is the Scala shell plus some extra, so they're just sitting on top of the Scala shell. So a lot of things you get from there. They come from the Scala shell. So all right, we started up our interactive shell. So before we sort of go into the examples, just a quick review, or maybe first time, if you haven't done any functional programming, of some of the things we're going to use in this. So Scala, functional programming language, one of the big things are these high-level functions that I can, as argument, give another function to, and it sort of does work on the whole collection. So one of the most basic ones is called the map function. And basically what it does, it applies the function that I give it as an argument to every element of the collection, and then returns to me a collection with those new elements. So basically what we're saying here is, let's say I have a list of type A. So I have a bunch of things in there that are A's, maybe strings or something like that. So in my map function, I got to give it a function that as an input takes an A, something of type string, and then it can return something of type B. It could be the same, it could be another string, and we'll see some examples of that here in a second. But for every A, I'm creating one B, and I'm creating a big new list that has all the B's in it. And I have one B for each of the originals. So the original size and the size that gets created afterwards, those two lists are the exact same thing, but they now have a different content. So, so a Scala example here. The first thing I'm doing is I'm defining a function called compute length, and I give it a parameter W, which is of type string. So in Scala, if you've ever done Java, you have string W. In Scala, you have W colon and then whatever the type is. And that function returns something of type integer, an int. And what I actually want to do in that function, I want to take the W and compute its length. W is a string, and it's in Scala, sits on top of Java. So it has all the Java API, so that's the length method on a string. So now I have my words, which are just a list. When shall we three meet again? And Scala basically infers types, so I don't have to say, hey, this is a list of strings. It knows that these things in here are strings, so it's like, yeah, that's a list of strings. That's what it's telling me there. And so now I do a words.map, and I give it the compute length function. Words takes a bunch of that's just a bunch of strings. The compute length as input takes a string. And so now it applies that compute length method to each string in the original. So when is 4 characters long, shall 5, we 2, and so on. For each object in my input list, I have one object in my output list. Input list is strings, output list is ints. So that's what map does. So that's a little bit long to write. So we have all this syntactic sugar, and you'll see a lot of this when you start looking at Spark. In Scala in general, it's like people don't want to type a whole lot of things. So one of the things, functions are first-class objects. I can pass them around. So I can say val f. So I'm declaring a value, an immutable variable. That's a val. So f is just a function that takes a w, which is a type string, and returns the w.length, which is a type int. So then I can apply that function to my words. But hey, why even create a function? I'm just creating the length. So I'm just going to use an anonymous function. So I'm just going to say map, and I'm going to give it w of type string, return the length. But hey, the compiler can infer all the type arguments, so let me not even tell it that it's a string. It knows already, so I can just say words.map w, and then give me w.length. Or if you want to do ultra short, like positional arguments, you can just use this underscore. And it just figures out, hey, I have something, and it's an underscore, so it's positionally matched if you have more than one argument. You have like 2 underscores, and the first underscore is the first argument, the second underscore is the second argument, and so you get this underscore dot length. And that's as short as it gets. So, and you'll see sort of all notations, and you pick whatever is the most readable for you. I sort of like that list 3. Underscore, once you get used to it, it's okay too. But, I think readability is still a must if you want to maintain code. You can get too short. So the other thing we're going to see in the code is an option class. So, null pointer exceptions. You know for sure something's not null, but it really is, and you get the null pointer exception, which is like a runtime exception. You have no clue whatever happened. The null pointers, null, just a bad concept sometimes. So the Scala guy is like, all right, we're going to replace that with an option. An option is something, an option of type t can have 2 values. It's either something, so it's some t, or it's none. None means it wasn't there. Some means something was there. And the nice thing there with functional programming, that option can be treated as a collection. So it's like a collection of one element, almost, and you can iterate over it. And if you're so one of the things that's really nice, Scala integrates with Java, and so you might have a lot of null pointer exceptions. So you can do option null as just none. So the next method is a flat map. And I'm not going to go into too much detail. Again, you give it a function, but this function has a different format. It takes something of type A and gives me back something that's gen traversable once. What is that? Well, it's something that can be traversed once. It could be like a list, an array, an option, an iterator. But it takes one element, and instead of giving you one element back, it could give you an empty list, a no element back. It could give you one element in a list back, or it could give you a bunch of elements back. And then the flattened part of the flat map is it then takes that general traversable once, if it's like a list, it takes every element of that list that you just generated, and it puts it in that output list B in the order they were generated. So it removes that inner nesting, and the output list can be smaller, the same size, or it can be much larger. So in the flat map example, if I do the split, I have this line on Macbeth, which has a new line character. I'm splitting on a new line character, just like a Java function. So I have an array with 2 elements, 2 strings in it. If I call a map on that array, further split each line by this non-word character split, then I get 2 arrays inside of my array, so I have this extra nesting. But if I do a flat map, it removes that extra nesting, and I just get an array with all the words that were from all the lines. So if I ever wanted to do word count, that's probably what I want to look at. So tuples is the other thing we like, right? Key value pairs. Tremendously useful for doing data science. Everything has a key, and then there's value associated with it. In Scala, you can just use this notation where you use the parentheses. The first thing is your key. The second thing is your value. It's a tuple. If you want to access it, it's tuple underscore 1 gives you the first thing. Tuple underscore 2 gives you the second thing. Or you can split it up by saying, like, you declare a variable val, key value is equal to tuple, and it will split it up for you in a key value. So when we started up the Spark shell, we automatically got this thing called the Spark context. So that's used for Spark to actually submit jobs, submit tasks, and connect to Yarn. If we run from the Spark shell, it automatically gets created. And in 1.3, we have the variable names SC for the normal Spark context, or you can also have a SQL context, which allows you to do that structured processing. And data frames, which is pretty awesome addition in 1.3. If you wanted to do a job that you actually submit, you could create a Spark configuration, just like a Hadoop configuration, and configure everything, like what the master node is, what the name of the job is, how many executors, and all that stuff. And you could submit that via the Spark configuration. Via that Spark context, you can also get your input. And you have accumulators and broadcast variables, which are sort of like the counters and distributed cache in Hadoop. So that's all off the Spark context. So then the RDD API, again, you have transforms and flat map filter, all those things are there. Lazy evaluation, nothing happens until you do an action. And then the action, count, collect first. We'll see some of those. So normal RDD you can already do a lot with. But if you have like tuples, you can actually convert your RDD into a pair RDD functions. And that gives you like by key. So you can group by key, reduce by key, aggregate by key. You can get the values, you can get the key. So there's some extra functions you can do. If your RDD is just numbers, you can have these double RDD functions, which like give you statistics and sum, average, all those things that automatically get computed for you. Or you can, if you have tuples, you want to sort them on the key, you could use these ordered RDD functions and actually do the sorting. So, if you've seen Java docs, this is a version of Scala docs. They have all the Scala information, and so it's sort of like Java docs with a little bit extra. So let's dive into the Spark shell. So the first thing I need to do, just because of the processing I'm trying to do, is I got to import RDD. So RDD dot underscore, that's the same as a star in Java. So it says like everything under that package imported into my namespace. I need that to do the RDDs. I want to process Avro, so I got to import some Avro classes. I need the Avro key and the Avro key input format and a null writable, because that's how I'm bringing things in from the Hadoop API. And then I need to know about my mail record, so that's what the next couple imports are about. So let me just see what. Okay. This one. And don't worry, I'm not going to type. It just wouldn't happen. So I'm just going to copy this, come over here, and paste. And So now, good, I have all the imports that I need. So now the first thing I want to do is, I want to read in, actually, let me make sure I'm following script. I just wanted to show you on the shell itself. So if you do like sc.tab, it has command line completion, so it will show you like for a given object, like what methods are actually available on it, which can be pretty nice. And it also has, command history, so if I have an up arrow, I could rerun a previous command. So that's just nice things about the shell. Exit will get me out of it. All right, so now what I want to do is I want to read in Enron Avro file. So this is, I created from those 500,000 emails, I created one big Avro file that has all 500,000 emails in it. And actually, this is a subset on this Docker image. I don't have the full set. I think I have like 191,000 or something like that. But essentially, in order to read it in, I need to use on this SC, so that's my Spark context, I want to call that new API Hadoop file function. And in order to use that, I actually need a Hadoop configuration. So I can, on SC, I call sc.hadoop configuration to get the Hadoop configuration. And then I call this API, I want to read in the enron.avro. And since I'm running as root, it's actually going to look under /user/root in HDFS. And that's where my enron.avro file sits. And how do I want to read it in? I want to read it in with the Avro key input format. And it's going to be an Avro key input format of type mail record. And the key is going to be an Avro key of type mail record. The value is going to be a class of null writable. And I give it my Hadoop configuration. And from that, it generates the RDB for me. And I'll just, in the interest of time, I don't know if I should show you in the shell. I'll show you a little bit something in the shell, and then I'll come back to the slides. It'll be a lot faster. But just so you trust me that this is actually how it's happening. So I do this. Control D, and it actually executes it. So the first thing I did was read in that mail records Avro RED. So, and essentially when you read that in, you get this thing that's a tuple, and it's sort of like a key value pair, like you would in a mapper. And the key is an Avro key with a mail record inside of it. And the second part of the tuple is a null writable. Well, that's ugly. I don't want that null writable. I don't want the Avro key. I want the mail record. So the second thing I was doing here, and I created this records RDD, is I go through the mail records Avro RDD, and I apply a map function. And in that map, what I do is I pull out from the tuple, I pull out the Avro key, and then there's a function on Avro key.data, which actually gives me back a mail record. So I now have an RDD of mail records. Good, that's going in the right direction. And rather than showing you some of this stuff, I'll just talk about it. So the next thing I got to do, so now I have my records RDD. The next thing I want to do from those records RDD, I want to pull out the username, and I want to pull out the folder name for that email. But, it's always like you don't know for sure if they're there. So I have this mail record.getMail field option with the username and the folder name. If it's actually in the map, it will give me a sum with the actual string inside of it. If it happens not to be in the map because for that email something didn't parse right or something, I always want to account for failures, the option is going to be none. And so in my if statement down here, I then check to see, hey, is the username defined? Is the folder name defined? If so, then give me back some username option, comma folder name option. That's the tuple. else give me back a none, but I'm putting it through a flat map. So the flat map takes the little option as a collection of 1 and takes the thing that's inside of that option and puts it into the output. So it basically strips the option. So it's kind of a neat functional programming trick if you're into that stuff. So now, once I have all that, I'm going to cache. And so at this point, I read something, I'm telling it, whatever you're reading in, put it in memory. But everything I've done so far, flat map, and cache, those are all just transformations. That means nothing has actually happened. These things are executed lazily. So I got to execute an action. And the action I'm going to take is I'm going to count how many of these tuples I have in the tuple RDP. And that's an action, and that causes all the lazy transformations to execute. So let's see what that actually looks like. And I'm going to do it twice. And so now you see that little stage thing at the bottom, so something's actually executed. Now, this is a good time to look at the, and it comes back 191,000 as the result there of the last thing it was executing. But one of the things I can look at now is, and you're familiar with this, so this is my Hadoop cluster. I'm running, so I'm looking at my resource manager. And on that resource manager page, I'm running this application, and that application happens to be the Spark shell. It's running on there. And has its own tracking UI, its own application master. If I follow that link, I'm going over to the Spark web UI. So the Spark web UI tells me, hey, for this particular job so far, I executed 2 jobs, the actual actions, 2 counts. The first count took 7 seconds. The second count took 2 seconds. Why is that? Because the very first time I executed, remember I told it to cache. That was like the last thing I did before I actually did the count. The first count caused the whole RDD lineage to be executed. So it executes that job and then takes the output of that and puts it into memory. So when I execute the second job, the second count, I already have that stuff in memory. I don't need to read it from the file system. So, for this trivial set, it's not that big a difference. But if you have, like a lot of executors running that are doing tasks in parallel, it can be quite a difference. So from here, from this UI, you can see, what were these actual jobs? You can get some statistics. How long did these things take? And how much memory did they read? And how many partitions? And how much stuff they wrote out? So you have all that. You can look at the storage, which tells you, right now I have the usernames and folder names for 191,000 emails. They're stored in 28.4 megabytes. You can look at your environment. You can set like all sorts of options, and you can look and see what your executors look like, and actually look at the logs that they're writing down. It's kind of nice, useful UI to look at. All right.
Can I ask a question?
Yes.
What's the difference between cache and checkpoint that you mentioned before?
So cache puts it into memory. Checkpoint would write it back out to the file system.
Great.
Yep. And there's also persist, and you can put some stuff into memory. You can choose how it's serialized. You can serialize some of it to disk. So there's lots of different options. But cache is like the memory option. If it wouldn't all fit into memory, it would spill whatever it can't fit into memory to disk. So we talked about that. So now we have an RDD of tuples. And with that tuples RDD, I can actually now do some work. So what happens behind the scenes is I have an RDD of tuples. Scala has this concept of implicits. And basically what the compiler said, I'm calling, later on you'll see I'll call an aggregate by key method on this RDD. And the compiler says, wait, this is an RDD, it doesn't have an aggregate by key. Let me see if there's an implicit in the current space that would take an RDD and convert it into something that has that function available. So it's a little bit of magic that goes on behind the scenes. That's used, in small doses, quite powerful. If you go crazy, you're going crazy, and that's never a good thing. So here are the pair RDD functions. So if I have tuples, key value pairs, I could return an RDD of just the keys, the values. I can run a map on just the value, a flat map on just the values. I can group by the key. And so I get a key and then all the values that are associated with the key, which is an expensive way of doing it. The reason for it is you can't do any combiner. Like in Hadoop, you have a combine method that you can basically run to, like, in that partition, sort of combine a bunch of values before you send it over the shuffle. If you do a group by key, there's no local combination. All the key value pairs get sent to a different partition. And then usually, you then want to do a reduce or some sort of aggregation function on that iterable anyway, but you paid for the price of sending everything over the shuffle. Whereas if you use reduce by key or aggregate by key, it tries to do the local aggregation first in your partition, and then only shuffles the aggregated values. So it's much more parsimonious doing it that way. And then you can do a lookup where you give it a key and then return all the values, and you can do joins. Like joining data sets, you mentioned it earlier, to me, it's kind of painful to do. But in Spark, you just create a key value pairs, and then you can join them with other key value pairs. And Spark takes care of doing the right type of join. So it just makes it a lot easier. So the unique folders by key, basically what I'm going to do is I'm going to aggregate by key. And the aggregate by key method, so as its first argument, takes like a zero value, if you will. So my zero value is an empty set, an empty mutable set. And then it takes two functions, a sequence operation, which gets run in each partition, and then a combination operation, which takes the result of each partition and combines it with the results of the other partitions. And so in each partition, what I want to do is I want to take my folder and then add the new folder to it. And since it's a set, those things are going to be unique. And then as my combo op, I want to take all the sets that I created in each partition and just add them together. So now I know how many unique folders each user has. Of course, what I really want to know is just the size. Right? I don't care what the folders are. I want to know how many of them they have. So I'm mapping just the values. I'm taking the set and outputting set.size. So I know for each user now how many folders that they actually have. Now, if I wanted to do some data exploration, that's the nice thing about the interactive shell. I have all these methods that are available to me. If I want to see what the data actually looks like, I can just call the first method. And it just returns to me one value, but I can actually see what it looks like. If I want to see everything, I could do a collect, but that brings everything back to the driver. So if you have a big data set, you're going to run out of memory. So you can do a count, or you can take just 3. And it'll take the first 3 from wherever. You can figure out what the max value is. So here, on this folders per RDD user, we did the max, and then the ordering that we wanted to do was by the second part of the tuple, i.e. the actual number. And we find out this guy, Keen, or gal, I don't know, Keen S, has 193 mail folders. Talking about organized. And then, this person, Harris, S, they have the minimum with just 2 folders. But, sometimes I have a really big data set, and I'm just going to get a feel for what's actually inside of it. That's, of course, where sampling comes in. So I can just say, sample this RDD. Don't replace anything. That's what the false is about. So with no replacement, and it gives me, like in this case, I want 10% of the original on a randomly sample. And so I can downsample and see what things look like. So it makes it all very easy. And then, of course, I have these double RDD functions where I can figure out what the mean is, the standard deviation, the stats overall, the sum, histograms. So what I can do is, for the folders, I just take the values. So remember, right now, what we have in this folders per user RDD, we have the username, and then how many folders they have. So I just want to find out how many folders that they have. So I'm just using the values. And then that is an RDD of type integer, which means it can be converted to the double RDD function. And I now have a stats method available. When I run that stats method on the folder count, I find out I have 40 different samples. The mean, so the average number of folders was 30. Standard deviation 37, because there were some outliers, so to speak. The max was 193 folders, and the minimum was 2 folders. So this is, I don't have to do a whole lot of writing of anything. It's just available to me. And I can then check it out in a histogram to see what the actual distribution looks like. So I have this histogram function. I tell it what the buckets are. So, my first bucket is 0 to 25, 25 to 50. So 26 people were in the 0 to 25, 5 in the 25 to 50, and then 1 in the 175 to 200. And all those nice high-level functions that are built in. And then when I look at the RDD lineage, so in order to get to that folder counts RDD, I had to start all the way at the bottom, and I created this new Hadoop RDD. So that's what I read in from the file system. So then it got, you were asking about like how these things get created. So then I have a map RDD where I took out that Avro key and just got the mail record. Then I did a flat map where I created the tuples, the username and folder tuples. Then I aggregated by key and created this shuffle RDD. So shuffle RDD actually means it had to do some sorting across the network. Then I mapped the values and got the map RDD. So that's the lineage of the whole thing. So, just like in Hadoop, when you do a reducer, remember the key values are reused, right? You have like text writables or something like that. It reuses the same text writable, so if you want to cache off those values, you actually got to make copies of those things. Well, if you're using the Avro input format and you wanted to store or do something with the whole record, you need to make a copy of the record, and that's sort of what this code is showing. So, hopefully that sparked your interest, unintended. There's some resources there. You can look at the code, but also at O'Reilly, I think 2 really great books, The Learning Spark, which is basically by Databricks people, Holden Corral, Zaharia, I don't know how you pronounce his last name, but he's the PhD dude who actually came up with the whole thing. And then I guess the guys in Cloudera wrote the other book, Advanced Analytics with Spark, and that's Sean Owen and Sammy Uriza, I don't know how he pronounces his last name. But also coming, and this shows you how much interest there is in this right now. There's 2 upcoming MOOCs on machine learning with Spark in Python. They're coming this summer. They were supposed to start in April, but now I think they're like June or something. Stuff always moves to the right. And if you wanted to learn more about Scala, there's actually 2 Scala MOOCs by Martin Dursky, sort of basic and an advanced one, which are really excellent. And then if you go to the Databricks website under developer resources, they have all sorts of videos from the Spark Summit. They now just had a Spark Summit East. They always had one in San Jose. They just had one in New York City in March. They taped all the videos. So lots and lots of resources. And the homepage, the Spark Apache homepage, also has a lot of good resources. So that's all I got. Questions? Oh, yeah.
On that course you just mentioned it there. So I just put, do you know the default or where they're from? Typically Spark and
I'm not sure what they're called. So Coursera, like the search didn't show anything?
Just having Spark, I'm not sure.
Okay.
Machine learning.
Yeah, maybe search under machine learning. Yeah, I signed up to be notified when they come out, but I don't remember like exactly what they're called. But they're both in Python. I think one is a Berkeley guy. I don't know who the other one was. Well, I can probably find it. All right. Any other questions? Sorry, that's what I have to put on the gas pedal there. You know, it's like whenever you do demos, it just takes so much longer than.
I can't imagine covering this last time.
So at the beginning, you configured or defined like an executable memory and a node memory. Which one is used for the caching? I assume the executable.
It's on the executor.
Yeah, executor.
The executive memory. So you can have like a bunch of those. You have one driver, but really the data set and the partitions, they're stored with the executor. And I forget exactly, there's like a percentage of the memory. Like if you say, I want to give my executor this much memory, percentage of it is basically allocated to storing the RDD. And it's actually configurable. Any other questions?
Do you have an opinion on the Python API?
So the Python API, not strongly typed, obviously, but I think originally I heard that was always a little bit lagging. Now they're really trying to keep everything nice and fresh, and you can do all the same things with Python. That's what I heard. Now I'm not a Python user.
That's what I heard.
So,
You try the
so I just started playing around with data frames, and I'm sort of working on a little tutorials actually using data frames. So there's a Databricks published a Avro library that allows you to read in an Avro file and make a data frame from it. And it's a very nice API. I can show you real quick. So, basically here, I just do the SQL context. In the middle, you have that records EF. And so then I can say records EF.select from, so I'm not even using the SQL, but you can use that DSL, and then it's called distinct on it, and basically figure out, how many unique froms there were in the whole field, in the whole data set. So it's very, very powerful, even just as a DSL. But then you can also register things as a table and sort of run like Hive SQL statements on it. So, and underneath the hood, it's all sort of works like an RDD. So you can really, use everything like all the map and everything. So it all works seamlessly together. So it's a really nice API. And if you use instead of Avro, use like Parquet. They really have these optimizations in terms of reading things. So it figures out which fields do you actually want, and then in Parquet, since it's a columnar store, you can actually skip columns, and it pushes that all the way down, and apparently makes the query even that much faster. So it's a nice addition.
Is Avro the only way Spark communicates with Hadoop?
Oh, no. That's just what I use. So there's like if we look at the RDD, the Spark context. So that's how you would actually communicate with things via the Spark context. And so it has all the Hadoop RDDs. So you see how this is the original Hadoop API, but you basically just specify the input format. So I was using the Avro key input format, and that allowed me to talk to Avro. But if you wanted to talk to Accumulo, you would use the Accumulo input format, whatever HBase uses. So whatever you can talk to from Hadoop that you have an input format for, you can easily do from here via that. And it also has a couple of methods like text, so sequence file, if you want to read from a sequence file. So you don't even need to go through all that input format stuff. If you wanted to read from a text file, then you just say text file, and you give it a path. And the nice thing there is, for testing, you can read from a local text file. And you just give the path to your local text file, and then you can run that in a cluster, and it will try to read a text file from HDFS. So it has other methods and input methods. But in general, whatever input format you have, you can read from it.
All right, thanks.
All right, well, thank you.
All right, thanks for coming, everybody. The place that we've decided on is Of Love and Regret, which is a block west of here. So if you want to come out for drinks, come out. If not, thanks for coming. Make sure you tell your friends and everything. And thanks, AWOL, for hosting.